In the last video, we saw how we compute the length of a truss member and the angle of a truss member. Now we think about how can we measure the deformation of this member. So it's obvious that only the change in length of the member contributes to deformation and not the rotation of the member as a whole. One possible way of thinking about deformation is change in length over original length, as we're familiar from our undergraduate mechanics. But this definition creates problems for very large changes in length. For example, if we take the member and squish it all the way down so that its length becomes 0, then this definition would give us a deformation of -1, whereas we would prefer a deformation of -infinity for this extreme case. For these extreme cases, we would like, if the length is infinity, so if we stretch it to infinity, we want the deformation to be infinity, and when the length is 0, we want the deformation to be -infinity. Such extremes seem to be artificial and just theoretical, but such large deformations are important when we deal with materials like rubber and other polymers that deform a lot. One definition of deformation that does the job is based on the logarithm function. So we define this function epsilon log of u as the log of L of u divided by L. And the log function appears naturally in many other situations. For example, musical notes follow a logarithmic scale. So if x is small, then we can show that the log of 1 plus x is approximately equal to x. We can see this graphically like this. So this curve is the log function, and the straight line is the x function. So near x equals 0, we see that log of 1 plus x is approximately equal to x. Later we'll see that this is called linearization. So epsilon log of u is log of L of u over L, which we can write like this as log of 1 plus L of u minus L divided by L, which is approximately equal to L of u minus L divided by L if the change in length is small. So for small changes in length, we see that our original definition approximates the epsilon log definition. We call this change in length over original length as epsilon BO. Another possible approximation of epsilon log is like this. We write epsilon log as 1/2 of the log of L over L squared, which again we can write as log of 1 plus this quantity. And this approximation is called the Green-Lagrange strain, which we'll define as epsilon GL of u is 1/2 L of u squared minus L squared divided by L squared. So epsilon log, epsilon Green-Lagrange, epsilon BO, these different measures of strain have significance in 2D and 3D, as we'll see in assignment 2. We'll see, for example, that in 2D and 3D, epsilon Green-Lagrange is simpler to compute and is a good approximation for epsilon log.